Myself, D. Madhuranthaka, working as assistant professor in IARE, Dundigal, Telangana. So today's lecture is on graph theory. So we will discuss the importance of graph theory subject in day-to-day life, and this subject has a wide range of applications in real time. Any problem in the world can be modeled by means of a graph theory. So everybody thinks that graph means it is a representation of the variables, maybe a variables of number 2 either in x-axis or y-axis. Okay, so that is related to know the variations of the one parameter with respect to other parameter that can see in the laboratory. And this is a purely technical subject. Right? It's a combination of applied mathematics and all engineering disciplines as well as science subjects and mathematics. Now we'll just see what is graph theory, right? What are the applications of graph theory? So I'm just saying that all the problems in the real world can be modeled in graph theory. So take one example. If you want to move from national capital to each capital, suppose from Delhi to Hyderabad, Delhi to Bangalore, or Delhi to Tamil Nadu, Delhi to Kerala. So what are the constraints here, right? So then how do you model this type of problem in graph theory? Here the constraint is one is time, another one is distance, right? And we'll go in detail, right? Each and every application of graph theory, right? After knowing the terminology. In graph theory, we have basic 3 requirements to be fulfilled. First one is you should be familiar with the terminology in electrical and communication engineering as well as in electrical and electronics engineering. We have graph theory subject. Whereas that graph theory deals with voltages and currents, right? Whereas this graph theory is not of that kind. That is the reason. Don't be, and in mathematics also we'll be having x-axis, y-axis, which are at 90 degrees apart. So this is a universal subject, right? So all the problems that I have given a simple statement, all the problems can be modeled, right, by means of a graph theory. Then I'll just list out the 3 requirements now. The first requirement is we should be having a familiarity with the terms. Suppose if you want to speak in English, we should have a vocabulary, we should have a word power. Similarly here also, we should be having a familiarity with the terms used. Almost 60 to 80 terms are used, right, in graph theory. And the second one is once and learning of the concepts of the algorithms, or you can say that analysis of algorithms. Once we know the concept, so many algorithms are there in literature. Suppose take an example of A star search algorithm or DIGRAPHS algorithm. A star search algorithm is used in Google Maps, right? To understand that A star search algorithm, you must have the command over the terms which are used in that algorithm, right? So that is the reason the first requirement is knowing or understanding the terms which are used in graph theory. It's about 60 to 80, right? And the second one is analysis of algorithm. So okay, we have algorithm is of only 5 to 7 steps, right? Right? We have different applications. I will go in detail one by one, right? And remember, this subject is not restricted to mathematics. This subject is not restricted to computer. This subject is not restricted to only engineering disciplines. It is universal subject. And the third requirement is, so whatever the algorithms that are there in the literature for different applications, we have to develop a program. That means a software, right? So we have different languages readily available. We can write the program either in C language, we can write the program either in C++, we can write the program either in Java, we can write the program either in C#, we can write the program in Python, right? So it's our option, whichever the language you are comfortable, you can proceed with that language, right? So these are the basic 3 requirements to be fulfilled, right, to understand or to have a command over the graph theory. And this graph theory is normally playing a vital role in high and high paying salary. Offering jobs, high paying salary, offering job companies are recommending this graph theory because I have given the simple statement. This graph theory is having a applications, right, which are in real time. And see another application. The first application is related to distance, and second application, if you want to lay a cable, right, assume the telephone cable. So nowadays the telephone, landlines are not there, but so we just taking an example, right? So your house is somewhere, assume that nearby exchange, right? What is called telephone exchange. So we have to select in such a way that, right, but there is no proper connection from your home to that exchange. And if you want to get a connection which are already having a what is called poles, so we have to assume that pay a lot of money because of the larger distance. So this also gives the solution. This kind of problems also have a solution in the graph theory. And the next one is, suppose 100 jobs are there, right? So we have to fill only 100 people for that with maximum utility. Maximum utility means assume that there are 500 students. So how to assess their capacities, right? So we'll be having various methodologies. So using those methodologies, maybe written test or group discussion or some other, right, personal interviews, you can select one person for a given job, right? But this is also another application. And the next common thing you can see nowadays, Amazon and Flipkart boys, right? Suppose they have to deliver a product at one point. After that, they have to go to another point two. After that, they have to go to another point three. Assume that at the all of a sudden he identified that one good is missed, right, which is to be delivered at point one. Then what he has to do? What he is supposed to do? He has to come back to 1.1. So that means he has to complete all the deliveries, right? Right, product deliveries, right, without having more mileage. That means it has to cover all the places with the minimum time and minimum distance. So this is called traveling salesman problem. And the next one is colors. How many colors are needed? How many colors are needed, right, to differentiate? You know that in the world we have 195 countries, but we don't use 195 countries to differentiate each and every country in the whole map, right? But only 5 colors have been used. 5 colors have been used for certain things. That means ocean we have to use only blue only, right? Right? Like that, yellow. So you can see green. For hills we have to use green only. Only 5 colors have been used, right, to differentiate one country border to another border country, right? This has been introduced by Peterson, and hence this application is known as Peterson graph. And these are the a few applications. Just see that title itself. These are few listed practical applications. We have numerous applications of graph theory. Due course of time, you will be able to see what are the applications, how you learn. And see, the first new term introduced here in graph theory is graph, right? A graph, G is a symbol used, but we should be very clear about the symbols used also. The reason is behind, to understand the algorithm, suppose they use some P, sometimes they use K. We don't know what is the meaning of P. P, you cannot see that P means carrot, K means something like that, right? So we should have the familiarity of the subject, definitions, terminology, and the symbols used, right? The graph is normally represented as Z, is a triple. Triple means 3 parameters will be there, consisting of vertex set, it is called VZ. Another one is edge set, that means E of G. E of G means E means edges, V means vertex, right? So this represents the graph. And the relation between these two, that means, or else you can say that association between vertices and E. This is what, right, called. So we can say that, suppose take a simple graph having, you can say that so this is having 1, 2, 3, 4. That means 4 edges are there, right? These are called ABCD. ABCD means those are a connection between node 1 and node 2. That means this is called H. So the association between node 1 and node 2 and this one is called, right? You can see the definition. A graph is a triple consisting of vertex set and edge set, and the relation that associates. So what is the relation between node 1 and node 2? In node 1 and node 2 connects the edge B. That is the relation. Or else you can say that edge B is connected between the node 1 and node 2. That is called the relation. Right? So graph. Now we started with a definition. So we can use the commonly, and so make a habit of reading textbooks to learn a new subject. So Introduction to Graph Theory, Douglas W. Best is the common popular book. Douglas B. Best, right? Pearson publication. So this is a common book. And another author is John A. Bondi and U.S. Murthy. So this is also graph theory with applications. First one is Introduction to Graph Theory, Douglas W. Best, Pearson Education. Another one is Graph Theory with applications. This is not restricted to only engineering. So this is Murthy. These are the two popularly used books, right? Make a habit of reading the textbooks to learn new things, right? And see here, so the graph can be represented by means of a diagram, right? And the next one is, so it is a new term, right? So how to represent vertex? Vertex means just now. So when you are learning a new subject, please remember, convert into your own language, as said by Vivekananda, right? Some Vivekananda Garu. So what is vertex? It's a new term, right? So vertex is represented by dot. So common term is dot, or you can say that point, or in electrical term you can say that node. So these are the commonly used terms to represent this one, right? But what is the technical term needed in graph theory? It is vertex. Similarly, edge. So edge means it's a line. Edge means a line joining the points. Right? Now we are in a position to understand what is meant by graph. Graph consists of edges and vertices. Edges are represented by lines which connects to, right, points. Those points are known as vertex. Right? So and remember, I have drawn a simple graph here. The same graph can be represented like this also. You can say that like this. This is 1, 2, 3, 4. Between 1 and 2 we have B. This is A, C and D. And now see the node point. There is no unique way of drawing a graph. There is no unique way of drawing a graph. But the relative positions of points, that means vertex. See, the first graph, it is looking like a rectangle, right? Whereas this is a circle. When I ask a question, both are same. Definitely, immediately as a student, your response is not. Both are not same, sir. How can you say that both are same? One is a square or rectangle, right? Another one is a circle. But in graph theory, we have to maintain the relationship between vertices and edge. Between 1 and 2 edge, what is the, between 1 and 2 vertex, right? What is the edge? B. Between 2 and 3, what is the, right, edge C? Between 3 and 4, what is the edge D? Between 4 and 1, the edge is A. Or you can say that, so between between 1 and 2 we can say that the edge is connecting, the edge A is connecting the vertices 1 and 4, right? So this is how we can understand the graph, right? Now it is clear, I hope, to everyone. And see, this is another definition taken from mathematics textbook, right? A graph, another way, is called a linear graph. Okay, so this is a representation z equal to v of e comma e. It consists of a set of objects. As already told, this information is taken from the objects or set of variables. Or see, another one is vertex. So v means vertices. Assume that the capital V is representing the objects v1, v2, and so on, vn. And similarly, edges e1, e2, and so on, en represents. So e, right? The graph is represented by a diagram in which vertices are represented as a points, right? As each edge is a line segment, right, joining the points or nodes, or we can say the end vertices. In this particular graph, see here how many 5 vertices are there and 7 edges. 5 vertices. For sake of convenience of understanding the concept, I have represented v1, v2, v3, v4, v5, v5, right? And how many edges are there? We have edges e1, e2, e3, e4, e5, e6, e7, right? So this is the basic definition of graph. And see the real-time applications. The following figures represents a part of roadmap. So this is one junction. This is a crossover, right? So we have a road from point P to Q and Q to R and R to S and S to T and T to P, right? And we have another road from P to S as well as Q to T. The same thing can be represented. This is a geometric representation. In electrical point of view, you can represent like this. So this is representing the impedance. This is inductance. This is impedance. Right. See here, the same graph can be, as already told, we don't worry about the size and shape of the graph. We worry about. So this connection can be represented like this. This indicates, so this, no, this is a crossover. Right. So this is a real-time application. This is also a real-time application. Right. Those are represented simply by a graph. As I already told, we'll just see the definition and we'll go to the real-time application. And then after having a knowledge and getting command over the topics, right, we'll see the various algorithms used for various applications. Whereas in graph theory 1, we'll discuss about 13 algorithms. Whereas in part 2, we'll discuss about 17 algorithms, altogether 30 algorithms, right? And the third part is implementation of the real-time problem by means of any of the convenient programming language. And see here, this is a map, right? This is one city, this is another city, Philadelphia, right? Belmore, New York. So now we are enjoying the Google Maps. When you type a simple message, suppose you want to move from Secunderabad to Vijayawada, it shows the time, right? It shows the time. And next one is, it asks the mode of transportation. Are you going by walk? Are you going by two-wheeler? Are you going by car? Are you going by train? The flight is not included, right? And see here, earlier when I see the Google Maps, you don't have such features. Suppose if you are traveling in a train also, you can see the speed at which the train is moving. So all these are apps. Okay. So all these are the applications of our graph theory because of this. So graph theory, uh, powerful algorithms, we are able to implement solutions for the most of the real world problems. Okay. And see, these are the few applications. Navigation, how effectively are using Google Map. Right? Don't have Google Map, you cannot go to the from one location to another location. Nobody knows all the cities in the world, right? And see here, so some of the algorithms just here it is we are using A star search algorithm. A star search algorithm. A star search algorithm is used for Google Maps. Some DIGRAPHS algorithm is there, that is for single source shortest path problem, as well as Bellman and Ford, right? Johnson algorithm, Rotowski. So many algorithms are there, right? So, and the next application is find the shortest path in road or rail network. And see, if you see one simple application, when you book a Ola, right? This is one mode of transportation, right? It shows some time, assume that 20 minutes, and 20 minutes, assume that 5 kilometers. When you book a Uber or some other, it shows 18 minutes and the kilometer is not 5, it may be 4 point. So same road is using, right? So the vehicle is also use the same petrol. But why it is showing a difference, right? We may tell the answer that there may be shortest path. It's not about shortest path. So the algorithm which is used in Ola is completely different compared to the algorithm which is used in Uber. So based on the algorithm, it assesses the various possible routes, right? And it shows the shortest path as well as the shortest time as well as shortest distance, right? So we have to see the constraints. You have to see the constraint if you want to find the solution for the real world problem, right? Once the constraints of the client is clearly understood, right, by the programmer, then we can have effectively definitely good software, right? And the next seating arrangement problem. Now we can see where do we find the seating arrangement problem. Just now I just given simply a statement seating arrangement. Now we can see that nobody stand in queue if you want to book a ticket for any picture, for any cinema, right? We'll have so many apps, right? So seating arrangement problem come into picture, right? So it shows where are the seats, where is the screen, where is the balcony, where is the pathway, and how many seats are filled, how many are vacant, right? So many things are involved here. So that is application of seating arrangement, right? And the next one is digraph. We'll discuss first what is meant by digraph, then we'll go to the applications. What is meant by digraph? So till now we have discussed about graphs. Our next topic in the graph theory is digraph. Digraph means we can don't think that two graphs. Normally di means two, tri means three. It's not of that kind. As already told at the start of the lecture. So we should have a familiarity with the terms used and we must have a in-depth knowledge of those definitions. Di means it's a direction. So technically it is called orientation. Digraph or orientation. If the edge is given, assume that this is a simple graph having three vertices and three edges. If the direction is given to edge, don't think that is a clockwise. Randomly I have taken, you can represent like this also. the directions are given to the edge 1, the direction is given to the edge 2, right? Then it is called digraph. Then what is the use of direction? Suppose we are at the junction, right? Where you can, this is a junction. Assume that if you go in this direction, we will go to so now I am at this junction. My target is to reach point C. My target is to reach, assume that, Calcutta. Okay. If I started my journey in this direction, because the directions are not given. Okay, it is simply a road. It is a road. This is also a road. This is also a road. I don't know how to go to C. Okay. So if I start unknowingly in this way, what happens? You will go to A, you never reach C. If the directions are given, if the directions are given, in olden days we have a milestone. For every mile, we'll be having a small stone which represents the number of kilometers and the nearby city. Right? So nowadays we don't depend on those. We will be having smartphones. You can use Google Maps. Okay. Or if you are going by four-wheeler, you'll be having a navigation also. Right? So that is the first one. The first one is that at any street or at any junction, if you want to move from that junction to any point, you must have a signboard in general, but it is not called signboard. You can say that it's a direction. Directions are needed or orientation is needed. And the next one is representation of the computer programs. Just a minute. Representation of computer programs. You know that you'll be having a start, some initialization, some conditions, some execution part, finally end. Right? If the condition satisfies, it will go to down, otherwise it will go back. So that means the computer do not understand if you don't give the flow of abstract. Right? And similarly, you can see the applications in electrical. So suppose there is interruption in one of the lines, how can they trace it? They cannot go in all the directions. They will check from one vertex to another vertex. If there is no copper connection between these two, then they will conclude that 1, 2, 3, 4. They will conclude that there is a defective thing, or some fault is there in technical word. Right? Some problem is happened in the line, right? Which connects the vertex 1 and vertex 2, which connects the from this place to another place. This is another application, direction, right? Another one is in electronics, sequential machines. So we can see most of the electronic applications use zeros and ones, right? And the next one is control system, right? System analysis and control theory. And before going to the next topic, right? I'll ask one question here. What is the biggest graph in the world? What is the biggest graph in the world? The biggest graph in the world is internet. We'll be having connection from one point to another point. We know the relation from one node to another node, or you can say that from this edge is connected between where and where. So the biggest graph is internet. So you have seen earlier seating arrangement, right? Yeah. This Hamiltonian has given algorithm to understand the seating problem. Just now we discussed about how to reserve a ticket for a given in a given slot for a given picture in a given theater, in the specific theater, right? And the another important thing is Euler. This is for utility. Euler is a father of graph theory. Is a father of graph theory. So he is basically a mathematician. And a politician also. Right? So he introduced graph theory to the real world in the 17th century. It's not a new subject, but it has got a lot of significance from 1930s onwards. And the wonderful thing about the graph theory is the concepts have been developed by mathematicians, right, and physics scientists, whereas the algorithm implementation, so many algorithms are there in literature, but algorithm implementation is carried out by a computer engineer. Computer engineer did not have only computer background, maybe having electronics background. So those who knows about the computer programming, then will be considered as a computer engineer. Okay, so that is a wonderful thing of this graph theory, right? So that is the reason it is used in image processing, it is used in social studies, it is used in biology also, right? So mathematics. Remember again, it is a universal subject. It is not confined to any discipline. So whichever, whatever you needed, you just understand and go for implementation. Now I have drawn the graph here. Now you can see 1, 2, 3, 4, right? 4 vertices. Fine. Edges A, B, C, D, E, F. 3, 6 edges. So I cannot store this graph. Right? This is a graph. So this represents a real time. This represents a real time problem. I'll give you one more example. Assume that 3 houses are there. This is house 1. This is house 2. This is house 3. This is water supply, gas supply, electricity. So you can say that H1, H2, H3, water, gas and electricity. These are the basic three. This is what I am just explaining utility problem in practical. I just given the definition and I explained about the shortest path in detail and Google Maps also and seating arrangement also. And now we will see what is meant by utility. Right? Every house needs water, gas and electricity. I don't want that person who stays in flat 2 do not take electricity connection from H1, right, or from H3. He has to have connection from directly from the source only, like this. Similarly here also. So now I represent the same problem by means of a graph. So this is H1, H2 and H3. This is water, gas and electricity. I want H1 needs water, gas and electricity. Similarly, H2 also needs water, gas and electricity. H3 also needs water, gas and electricity. So this is how we represent all the real world problems in the form of a graph, right? Once the real world problems have been represented, if you want to get the solution for, right, these real world problems, we have to feed this graph into the computer. But feeding the graph, nowadays we know that in YouTube, some millions of videos are being uploaded. Okay, the memories, we have abundant memory, which memory is it? But the problem is not that. We want the information. When you type something in the Google tab, you can see the time at which you have got the answer. Will it take 1 minute, 10 minutes? Earlier we have so many browsers, Bingo, Yahoo, Mozilla. Why Google is popular? If we type IARE, definitely we don't get only one page because it is established in the year 2000. Right? Every day they update the websites. Definitely will get some 20 plus documents related to IARE. But we want the document which is relevant to us. Right? But it don't take much time. It does not take much time. It takes very less time. So this is also a web application. Searching. The searching algorithm is also there in graph theory. Right? So those algorithms which are used by the outdated search engines, right, are not optimized, not giving optimal solution. That is the reason Google nowadays becoming a popular. Right? Here, the out of this discussion, what I want to conclude, right? We want quick and exact information, right? So instead of putting the entire content of the real-time situations into the computer, I'll just represent in the form of matrix. I'll just represent the real-time word problem in the form of a matrix. Once we get a graph or digraph or planar graph or non-planar graph, Hamiltonian graph, Euler graph, right? So many graphs are there. So that is what now next topic, matrix representation. Matrix representation of graphs and digraphs. Right? So matrix means normally we having rows and columns. This is you can say that Aij equal to some 1 and some 0 if it Ij belongs to some graph, not belongs to it. Right? So that means rows and concepts, that mathematical concepts are same. I'm not altering the mathematical concepts here. The only thing is in electrical engineering, in electrical network graphs, they use three things, that is 0, plus 1, minus 1 to represent relation between variables. Here variables means voltage, current. Similarly in electronics also, in the digital design circuits also, there is zeros, ones, plus 1, minus 1. But in graph theory, we use only zeros, 0 and 1. We use only 0 and 1. This is called binary representation. Zeros and 1. We will have hexadecimal representation, octal representation, decimal representation. Decimals means 0, 1, 2, so on, up to 9. Okay. So the use of zeros and 1, if we have a relation, right, between one vertex to another vertex, we have a relation from vertex to edge, between one vertex to edge, then we will represent either by 0 or 1 only. Either by 0 or 1 only. And there are two popular matrices which are commonly used. Let me give some time to erase these. We have two matrices, adjacency matrix and incidence matrix. And this is a traditional method. You just see, we have vertices U, V, W, X and Y. See the first line. The vertex U is having a relation with is having a relation with the vertex V and vertex Y. And similarly, the vertex V is having a relation between U, Y, and W. So this is also a complex thing. So traditionally they were using this one. Nowadays we use only zeros and ones to represent the relation between vertex and edge. Okay. So the advantage of representation, either graphs or digraphs, by means of matrix format, right, is first one is storage. Instead of storing the entire graph, I'm just representing, we have 5 U, V, W, X, Y, Z. Only zeros, ones, right? We'll see in detail about the adjacency matrix and instance matrix, right? The first one is storage of zeros and ones is comparatively takes less memory, right, with the storage of exact graph. And the second one is execution. You can say that speed. The execution is not at all comparable, right, compared to this graph and the matrix representation. Right? So this is about the matrix representation. So incidence matrix gives a relation between vertices and edges, whereas adjacency matrix gives a relation between vertices and vertices. I'm just giving outline what is meant by adjacency matrix and what is meant by incidence matrix. Incidence matrix gives a relation between vertices and edge, whereas adjacency matrix gives a relation between vertices and vertices. Right? So the vertex V is connected to how many vertices, it gives that relation. Or else you can say that another one is between this edge and this vertex, what is the relation gives by the instance matrix. We will see some problems on these two concepts. So before ending the lecture, so let us recap the concepts which we have discussed. We started at graph theory with some introduction, right? That means real-time examples of real-time applications of graph theory, and then graph definition. We have seen, according to Douglas W. Best, as well as per the mathematician, we have seen the two definitions and the digraph. So graph means we have to remember you can simply conclude it as graph is a combination of vertices and edges. And then we have seen the digraph and the applications of graph. We have seen Google Maps, seating arrangement and utility problem, and applications of digraph, flow, abstracts in the flow program, as well as street map and sequential circuits, control applications. And finally, we have seen the importance of matrix representation and what are the various matrices used to represent either graph or digraph. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.